Okay, so good afternoon, everybody. Welcome back to lecture number 15. So let me begin with, can you see the screen? Yes or no?
Yes. Yes, we see it.
Okay, how about this one? Now, do you still see it?
Yes.
Okay. Yes. So this example that I told you that you need to use engineering tools, it's not required, but practice problems 1 to 4, I think they are required. They're similar, and you may try to solve them. Okay? So last time we talked about what? Salient pole synchronous machines, correct? So last time I told you that due to the difference between the air gap, we will have two components that somehow equivalent to of f of x of s. The first one is due to the direct axis. The other one is due to the quadrature axis of the flux. So the direct axis of the flux would go here on the stator's south pole all the way here. The quadrature component is different, where it goes 90 degrees from, again, poles will change across the time, so this salient pole would rotate. So the quadrature after some time will be up, the direct after some time will be on the same quadrature side at a speed of omega, which is 2 pi 60. The phasor diagram, that what we need is we need to find somehow equivalent x of s, but we cannot, because you have two different x's, because you have two different reluctances. If you recall from last lecture, reluctance is G, which is the effective air gap, over mu A. So because of course, you consider the reluctance of the air only. You don't consider the reluctance of the steel, because you assume the steel would allow the flux to go. So your point of concern is this gap, this gap, this gap, and this gap. Clear? So due to that, we will have different x's. We will have different x values. So we will have reluctance of quadrature to be larger than the reluctance of the direct. So this implies reluctance is inversely proportional to the L, which is the inductance. You know that 2 pi f L would equal to jx. So this L is inversely proportional to the reluctance. It implies x is also inversely proportional. So you will have x of d larger or x of q? X of d. X of d will be larger. But how to calculate these x's? There is no easy way. There is no easy way to calculate it. But there are two ways that somehow in the textbook they use them. So the first one is through phasor diagrams. So here what they are doing is they are putting EF as the reference. V of t has an angle of delta. I told you last time this is what? This is a generator. Because if it's a generator, we will delta is positive. Now what's happening here is take the IA. So is this lagging or leading? It's lagging because V of t leads IA or IA lags V of t. So we're assuming it's a lagging power factor with an angle of theta. The torque angle is delta. So IA, you have to decompose it now into two components, the direct axis component and the quadrature axis component. So IA would equal to ID plus IQ. So IA is ID plus IQ in this single phase circuit. It turned out that IQ is in phase with IF and ID is 90 degrees with the EF. If you remember, there is a formula in E360, if I'm not mistaken, the MMF would equal to the change of flux. I don't recall the formula right now, but this formula states that the direct current, the current due to this flux, is 90 degrees from the induced EMF or EF. And because this is 90 degrees across EF, IQ will be um, in phase with EF. It's similar to Faraday. I think it's Faraday's law, the one that has change of flux with respect to time. The induced voltage would be change of flux. Change of flux is d in I dt. And with this would have a 90-degree phase shift. This would have a 90-degree phase shift. So if you ignore RA, let's say that we ignore RA. Let's say that we ignore RA. We will have the phasor diagram to be VT plus JIQ plus JID So that JID is 90 degrees away from ID and JIQ is 90 degrees away from IQ. So if you do all of this summation of the phasor diagram, I'm chasing the red line, all of this, you should get EF. So now let's ignore IARA. If you ignore IARA, after some mathematics, this is the final equation to calculate the torque angle using XQ and the power factor and IA. If you measure, you can measure IA, can know the power factor, theta, angle theta, and can have cosine and sine. You only need XQ. And how did they reach this formula? This math is hard. This is not required how to derive it, but this is method number one. Remember, we want to calculate EF and delta. EF magnitude is calculated using phasor diagram. This delta is calculated using the tan equation, and then you take tan inverse. So you can get delta to be tan inverse of this term. But how to do it? Math is hard. Take this figure without IARA. So clearly this is VT plus JIDXQ. Plus JAIDXQ plus JIQXQ, would have EF. From the phasor diagram, you will have VT sine delta. Where is VT sine delta? This is VT sine delta will correspond here. This is the delta would equal to X of Q times IQ, which is this term, X of Q, I of Q. No, VT sine is this. Basically, it's this component. Without the J, XQ, IQ would be equal to VT sine delta in red. It's very similar to the constant power thing that we discussed before. This would equal to IA times x of q cosine of the angle delta plus theta, or we call it psi. If you do that, you will scale IA with xq first. So IAXQ will be longer. And then you take cosine of this angle. So that's the projection. So this projection would equal to this projection would equal to this projection. This is how we start. Then take the cosine of psi or theta plus delta. This is plus or minus depending if it's motor or generator. Then you use the trigonometrics, math 002. Then you will have the flip of the sign, minus for generator, plus for the motor. If you have any question, feel free to interrupt me. I cannot see the chat. Then you will have VT to be IA XQ cosine over sine minus plus. This sign would cancel, this sine delta will cancel with this sine delta. You will have this nice term. And what are you looking to find? You're looking to find this delta. So cosine over sine is 1 over tan. And if you solve for this, you will have, first you have to move this term here. That's why you have VT plus or minus IAXQ sine theta here in the denominator. And in the denominator, in the numerator, you have IAXQ cosine theta. And this is the final expression. So the signs can be determined from the phasor diagram, whether it's a motor or generator. So this equation, I'm not going to ask you the problem on it in the exam. As you may see here, this example, which uses this equation, is not required, but feel free to explore it. I think it's a good exercise to explore, but I'm not going to ask you in the exam problems on salient poles. We just need to understand the concept. The other method, and this is more practical, this method is hard because you have to do the phasor diagram. This method can be done by taking different measurement. So from the phasor diagram, which is this phasor diagram, let me copy it. We'll take the attendance shortly. I know you guys want to leave. We'll take the attendance shortly. And I wouldn't check if you left or not. If you look at, for example, this phasor diagram, let's say we will have a component EF prime, which ignores the XID. It only says that EF prime is VT plus JID XQ. So this is EF prime. There is a typo here, so let's fix it. I think this is a... No, that's correct. That is correct. My bad. Look at this. EF prime is VT plus JIXQ. It's this phasor diagram. So we're using XQ and IA. This is IA, multiply it with JIAXQ, you will have this arrow from here, 90 degrees with some scaling. So VT plus JIAXQ would equal to F prime. Now define C to be the angle of delta plus theta, the angle of the torque angle plus the power factor angle. Then you will have, by definition, I of D to be I of A sine of delta, sine of psi. So if you take IA sine of psi, scale it down, you will have ID. So it's IA sine of this angle, you will have ID. So this ID equal to IA sine of this big angle, trigonometry. Then the delta of EF, which is that part, this part, the delta of EF, which is EF minus EF prime, clearly equals to what? Equals to this vector minus this vector. So this vector is JIDXD minus
الشاشة ما هي ظاهرة يا
J.
دكتور.
الشاشة ما هي ظاهرة. For how long كانت مختفي؟ Now
لسه.
طيب. Can you see it now?
الآن تمام.
طيب,
Yes.
let's go. So let's go back. So let me start again. This is the other method. EF prime is what? EF is VT plus JIAXQ. This is IA. Scale it with XQ and multiply it by J. You should get this arrow. So EF prime is this arrow plus this arrow. Define C to be the angle data plus the angle of the power factor. Then you will find the relationship that ID is nothing but IA times sine psi, trigonometry. Do it yourself. So 1, 2, and 3 are clear. Part 4 is, what do you want? Do you want EF prime or EF? From the title of the slide, you want EF. So EF is actually EF prime plus the delta. So let's get the delta. What is this delta? This delta from the phasor diagram is actually this arrow, JIDXD, minus this arrow, JIDXQ. If you subtract the two arrows, you will have the delta. So now, for me, I can add this term here. Maybe I can call it point number 6. Okay? Clear? So by knowing the direct current, is there a J here? Yeah, there should be a J. Okay? So it is JIDXQ, D minus JIDXQ, this vector. You should get delta F. If you combine them, you should get E of F. And is this magnitude or magnitude and angle? Your final answer should be what? EF at an angle delta, correct? This is the other method that is used. So you have two methods for salient pole to calculate EF and delta. All the equations are positive sign for the lagging power factor, negative for leading. The other thing that we wanted. Can you hear me? My internet just broke down. Can you still hear me and see the
Yes,
screen?
we can hear you.
Okay.
Yes, we can see it.
For a unity power factor, theta will be 0, so psi would equal to delta. The last part, if the machine is a motor, not a generator, because this is what a generator, EF is leading VT, delta is positive. The signs of lag and lead have to be exchanged together, so you have to flip basically the plus and minus to be minus and plus, minus and plus. Okay? What is the consequence? Why in salient pole we worry about EF and delta? For a very interesting phenomena that we will explore now. So this phenomena has to do with the power. If you calculate the power, start with S, where you will have, do you see my mouse?
Yes.
Yes or no? Do you see my mouse, Shabab?
Yes, we can see it.
So this complex power per phase or per unit, VTIA conjugate, where for some reason, if you define ID to be EF minus VT cosine delta over X of D, IQ is VT sine delta over X of Q. This is from the phasor diagram trigonometries. I know it's getting hard, but IQ is EF minus VT cosine. So EF minus VT cosine. If you do the math, you will note that you can write IQ as a function of EF minus VT cosine delta. IQ is VT sine delta over X of Q. If you substitute IA, which is the summation of the two complex numbers, you should get VT, which has an angle of minus delta with respect to the zero reference of EF, times the conjugate difference. This is not required. If you do the conjugate, this would be a plus. So ID is IQ minus JID. IA is IQ minus JID. Then you should have S to be this crazy numbers, which is P plus JQ. Take the real part. If you take the real part, which basically comes from this VTEF over X of D, and then the other part that comes from the sine 2 deltas, you will notice that the real power has the first term same as the round rotor. So this term, I'm going to put it in green. It is same as the round rotor. But the dangerous term is this one. Can you remind me? It's minus, I think this is also green, but this one is red. So the red terms indicating that there will be a real power without the field. Get it? So let's say EF is 0. There is no field. What will happen? This is gone. This is gone. But there is a real power due to the saliency. That's why P sub R from that rotor, due to the reluctance. Due to what? Due to the reluctance. And PF, the real power component, is due to field. So in salient pole motors, the real power has a component that's due to the excitation and a component that's due to the saliency or the reluctance. From this type, there is other types of machines that have been explored by changing the geometry of the rotor. They are known as, for example, switched reluctance machine, or in general, reluctance machine, which basically by varying XD, XQ, you can control the power, the real power. Keep in mind that we don't care about the reactive power, because even if EF is 0, there should be always a reactive power from the component VT square cosine delta square. If we were, what's the lesson that we learn here? The question that I will ask you in the test is, what is the difference between real power in rotor synchronous machine versus the real power in the salient pole synchronous machine? You should say in the exam, maybe you can write this equation, you don't have to write it, that we will have two components for the salient pole. One is similar to the rotor, which is due to the excitation. The other one is due to the reluctance or the difference between XD minus XQ. We call it PR from reluctance. Clear? Any other question? So that if you look at the power, you should have PF, which is the regular real power, torque angle at 90. This is the real power, the field due to field excitation. This is 90 degree. But here is the problem. We have a twice frequency signal, sine 2 delta, which is due to the saliency, or PR. This is R due to the reluctance. This would make the resultant power, the effective one, has maximum torque angle not 90 degree. Maybe somewhere, of course, between 45 and 90 degrees. Maybe this is 80. This is very dangerous. Why it is very dangerous? I'm going to ask by names. I'm going to ask Mr. Ali Abdul Latif. Can you hear me? Mr. Ali.
Hello? Yes.
So why this is dangerous, Mr. Ali? Why it's dangerous to have a degree maximum power at 80? We're
90.
losing. الحين في الراوند روتر الماكسيمم 90 صح؟
Yes.
السالينت بول بتصير أقل. What is the issue with that? Is this a good thing or bad thing?
I think it's a bad thing.
ممتاز ما شاء الله. Why it's a bad thing?
Because we may lose the
Synchronous.
stability.
So now here question in the exam. We call this the Ali's question in the exam. What's Ali's question in the exam? Which one has better stability range? Round rotor ولا salient pole? Ali, answer your question.
Oh, I thought it's a general question.
No,
Okay.
for you.
Repeat it again, please.
Which one is more stable?
Cylindrical.
Round rotor ولا salient pole?
Round.
Round, because its maximum angle is 90 and you're losing synchronism at earlier angle. Thank you so much, Ali, for answering this question. This question may come in the exam. Clear? So let's take the attendance for now. Remember, this is Ali's question. Study it for the test. So I'm going to take the sheet that you guys submitted to me last time. So those who were absent in the last lecture, they have to call themselves. So Mr. Osama, you have to talk. If you don't talk, absent. Khalid Saeed. Khalid Saeed. Ali. Ali Abdul Latif, you're here. Ibrahim, you're here. Dahwali
Yes,
here.
present.
Ahmed.
أحمد
البلو.
أحمد بلو زين.
Ali Alwan here.
موجود.
Let me check the names أسهل. Ali Alwan موجود. خلاص, I'll check the names. No need to say yes. If I don't find your name, I'm gonna call your name. Muhammad Aman, are you here?
موجود.
تفضل.
دكتور
Yeah, I will do your section. I read your names. Don't worry.
اسمي مو موجود بآخر ورقة كنت غايبة.
Yeah. I will add it. Don't worry. So is Murtaza here? Okay, we will have for the other section. I'm seeing all of your names. Okay, from the other section, I counted all of you are, I think, one absent only. Gahtani is here? No. Is Saeed here? Okay, Nawaf, I know that you were absent last lecture. Who else was absent last lecture? Yeah, okay, I added your name, خلاص. Zahrani, I added your name. Okay, enough. Let's focus on the lecture. So, can you see the screen? So XD and XQ, if they are equal, when they are equal, for the round, صح? Then we will have the old school equations. XD equal to XQ. A saliency part will be omitted. And XD is X of S now. So now what will happen? If the machine lost X excitation here, we will have still some real power. So I would say maybe it's better to move this part, maybe عشان to avoid confusion. Here. Okay? And I'm gonna insert an arrow for you because this is definitely will come in the test. I'm gonna put a star. Okay?
The PowerPoint
So,
didn't show.
oh, you don't see the screen? خلاص. Okay, now you see the screen. So you see the star? So this is star. If the excitation of the machine is lost, the machine will still have power due to saliency, which is the star part. Okay? This part. Okay. This is very dangerous. And for stability, I told you the round is more stable. This is for the round. So this example is removed. I'm not going to solve it, but clearly they're using the equation tan delta to calculate. They get tan delta 0.42 and then they calculate the delta. Then they calculate the C, which is this angle minus the power factor angle. Then here, the problem itself, find the power due to field excitation, means find PF. This is PF, find PR. This is PR. The last part, I think the last part is if the field current is reduced to 0. Will the machine stay in the synchronism? I think no, if I'm going to guess. So the output power is more than the power the machine can develop. The machine will lose synchronism. The last part is talking about shaft load removed before the field current reduced to 0. And you can solve it yourself. So now the last part of the slide. Today we have to finish the synchronous machine. Hopefully we have 10 minutes. So I'll take 5 more minutes if you allow me. Feel free to leave. So for the linear synchronous machine, a linear version of synchronous motor can produce linear or translational motion. So here, for example, instead of having stator and rotor to be in a circular mode, we're going to have the stator زي سكة القطار. Then we will have AC, three-phase windings. This is the train trail. And for the train car, we will have north-south, north-south. This is like the rotor, but it's not a rotor. It's the linear mover. So this is, and the air gap is actually a physical gap. This is from the high-speed trains that they use linear synchronous motors, for example. They are very high speed and efficient. So this is one of the application. And instead of the formula ns equal 120 F over P, you will have a different formula, which is velocity is 2 times the pole pitch. Pole pitch is the distance, the physical distance between the poles, or how many slots you count in the stator that would count as one pole. So they are powerful superconducting magnets that are used, operate at higher air gap. Currently, linear synchronous motor have not been used. Mainly, there are more linear induction motors used, but there is a demand going for linear synchronous motor in the field of high-speed trains, similar mathematical models and equivalent circuits for the linear ones. The other types of machines is the brushless DC motor. So this is a tricky one. So brushless DC machines is used for even small application. People think it's a DC motor, but in reality, it's not a DC motor. It's an AC source plus an inverter. What's the output of the inverter? AC. So this is like cheating. So brushless DC motors are nothing but synchronous motors connected to an inverter. And they are usually permanent magnet because it doesn't make sense to have field excitation. Just put magnets, call them brushless DC. They are very small, cheap. The idea here is you convert your battery output into small AC. So synchronous machine with permanent magnet in the rotor and operated self-controlled is generally known as brushless DC motor. Sensor, there is always a rotor position sensor that control the frequency of the AC supply, the firing angle of the inverter. So the rotor position, this is usually from Hall effect, goes back to the inverter and control. So this is self-controlled mode. They are very common and used in many applications, brushless DC motors. My favorite type is not the brushless DC motors. Well, the one used in the car, it's similar to brushless DC motor, but the inverters here have more control mechanism. So it's a synchronous machine plus some control aspect. My favorite part is to discover the magnets. There is 3 different types of magnets. There is first is surface mount. ايش معنى surface mounted? What surface? السيرفس حق الروتر ولا السيرفس حق الستيتر؟ It is the outer surface of the rotor. Clearly, they somehow glue the magnet on the rotor. What is the issue of gluing the magnet on the rotor? If you glue them at very high speed, those magnets would lose the glue, يطيرون. This is one of the downsides of the surface mounted magnets. So they are radially magnetized permanent magnets. They just glue them on the rotor steel, glue them. The relative permeability of the magnet is near unity. So we can say this is like round rotor. It's not salient pole. Why? Because the magnets, they are like the air. They are, the relative permeability, they are high, the reluctance is high. معاوقة حقتهم للمجال المغناطيسي. they're reluctant, like the air. It acts like large air gap. So think of this as air in terms of the magnet. So this is, so no need to have the salient pole. What is the drawbacks? The drawbacks is eddy current losses would go directly in the magnets and would demagnetize them. يعني لو كانت القوة المغناطيسية هنا شدة المجال المغناطيسي 4 تسلا, due to the rotating magnetic field, the effective magnetization would be maybe 2 Tesla. And over time, they would lose the magnetization characteristics of these permanent magnet due to heat. And here in the kingdom, having them would have smaller life cycle. So one other solution to avoid the issue of gluing is we call them the inset magnets. So we insert them inside the steel. We put here, so this is the rotor. We put a hole in the rotor and insert the magnets in, leaving them outside exposed to the air gap. So the air gap is also uniform here, all air, but we will have similar issues. But the benefit of this design is we can have higher speeds. And also there is, there is saliency in this configuration. Why there is saliency? Because the rotor is not uniform. The rotor is not uniform. Even though the air gap is a circle, think of this rotor as salient pole rotor. احنا نعامل الماجنت كأنه هواء. نعامل الماجنت كأنه هواء in terms of saliency. The same magnet size, they are usually higher than a surface because there is a reluctance developed. Type of rotor structure is more robust. The glue, there is no need to have glue. We still have glue, but they are inserted into the shapes. We still have negative effects of demagnetization. The last part of permanent magnet is the interior, which is my favorite one, is instead of having the rotor, just put them on the side, put some weird shapes like a star shape, fill it with magnet. Some people, they put the zigzag shape, similar to the other shapes of the stars. Some people put circles inside. So the floor is yours. And again, this is salient because the rotor is not pure circle. Clearly, we treat magnets as air, so this rotor is not circle. And the electric vehicles, they use this. EVs use this, IPM. If you open Delta, they use IPM, interior permanent magnet, or buried. And this arrangement can bury it into different shapes. Q-axis inductance is larger than D-axis. So this is clearly salient application. Due to the additional reluctance, the capability and surface placement are used in EVs and propulsion applications heavily. So maybe a question in the test, which of these 3 types use IPM, insect permanent magnet, or surface mount? You should say IPM is used. The advantages of brushless DC compared to induction machine, you will have smaller rotor size, higher power density, you will have lower inertia, faster dynamic response for vehicles, higher speed torque capability, lower cost, better heat dissipation, and better overall reliability. If you compare them with the DC motors, they have high efficiency because there is no slip, higher power and torque density, and lower operating temperature. I think this is just for your knowledge. Disadvantages of brushless DC. Brushless DC motor drive system, they require position sensor, so that's an additional course. If you remember the brushless DC here, we had sensors here. So those sensors would add a cost. Also, we need power electronics. We need an inverter and control system. This would increase the cost of the system, and demagnetization. of permanent magnet is also not favorable thing. So with that, we're done with synchronous machine. Here is some review questions. These questions, I might bring them in the test. So does change in excitation affect synchronous motor speed? Nope. Irrelevant. How about the power factor? Yes. Through excitation. Can be overexcited, underexcited, etc. What is a synchronous capacitor or condenser? This is overexcited synchronous motor. This is a review question. These are MCQ questions. Feel free to review them. Maybe they will come on quiz 3. So when do you want quiz 3? quiz 3 will be كيف؟ صوتك مو واضح حسام. When do you want quiz 3? Next Tuesday, okay? الأسبوع الجاي Tuesday.
Can you make it Thursday?
Thursday we might have online lecture, I don't know. بعدين في رمضان.
Sunday after.
What?
Sunday after.
No. Sundays doesn't make sense. We'll have it Tuesday. And then hopefully we'll have the mini major Tuesday before. The mini major is the fake quiz 4. One day before the major, okay? So if you don't want to do this quiz, you can do the fake quiz. Okay? Quiz will be easy, inshallah. Quiz 4 will be easy. Study these questions, the MCQs. So next lecture, we will start with the comparison. But let me verify. I think the title here is wrong. No. I think these are correct. These are correct. This is slip rings. Okay? So study these material, solve these questions, and this is the end of module 2. We're done. Any question? Do you have any question? So for the attendance, if I didn't take your attendance, let me know. Feel free to leave. I will stop the recording now.